Ever wonder how your phone knows exactly where you are at any given moment? I mean, how is it even possible to pinpoint one specific spot on this massive planet of ours? Well, the answer is this brilliant, totally invisible grid that's wrapped all the way around the globe. And today, we're going to decode that system, latitude and longitude.
You gotta love this quote, right? It's funny, but it also totally nails a huge problem. In a world as connected as ours, over there by the tree just doesn't cut it. We need precision. We need a single, universal language for location, what we call an absolute location, that works for everybody, everywhere. And that's exactly what this grid gives us. So how do we solve this global where are we problem? Simple. We imagined a giant grid wrapped around the entire planet. And this grid is made up of two sets of these invisible lines. You've got some that run side to side, horizontally, and others that run up and down, vertically. And here it is. This is basically our cheat sheet for today. The grid has two main parts, the horizontal lines, which we call latitude, and the vertical lines, which we call longitude. Now, each set needs a starting point, right? For latitude, that's the equator, and for longitude, it's the prime meridian. So let's break down how each one works, and we'll start with latitude. All right, first up are the lines that run east to west. Picture them wrapping around the Earth like giant hula hoops. These are our lines of latitude. Now, here's the most important thing to get straight about latitude. Even though the lines themselves run east and west, their job is to measure how far north or south a place is from one single starting line. And that starting line, it's probably the most famous line of latitude on the planet. The equator. Yep, that's our starting point, our 0 degrees latitude. It slices the Earth neatly into two equal halves. You've got the northern hemisphere on top and the southern hemisphere on the bottom. So from this one line, we measure up toward the North Pole and down toward the South Pole. And the way we measure it, super simple. You start at 0 degrees, right at the equator. As you go up, the numbers climb all the way to 90 degrees north, right at the North Pole. And as you go down, they drop to 90 degrees south at the South Pole. Oh, and since these lines run alongside each other but never ever touch, they've got a perfect nickname, parallels. Need a little trick to remember which lines are which? Here's a great one. I love this. Think of latitude as fatitude. These are the flat horizontal lines that go around the Earth's waist, kind of like a belt. It's a little silly, I know, but trust me, it's a super effective way to keep it straight in your head. Okay, so latitude tells us how far north or south we are, but that's only half the address. To really pinpoint a spot, we need the other half of our grid, those long, vertical lines that stretch from the North Pole all the way to the South Pole, and this is longitude. And just like latitude has the equator, longitude also has a 0 degree starting line. It's called the prime meridian, and every single line of longitude is all about measuring how far east or how far west a location is from this one specific line. So where is this prime meridian? Well, way back in 1884, a bunch of countries got together and agreed to run the official 0 degree line right through the Royal Observatory in Greenwich, England. And this line splits the world into two more halves, the Eastern Hemisphere and the Western Hemisphere. From that starting point at 0 degrees in Greenwich, we can travel 180 degrees around to the east or 180 degrees around to the west. And those 280-degree lines meet up on the exact opposite side of the planet, making a perfect 360 degrees circle. And these lines, we also call them meridians. Here's one more awesome way to picture the whole thing. Imagine a giant ladder wrapped around the Earth. The lines of latitude are the flat rungs you climb on, and the lines of longitude are the long side rails that run from top to bottom. It's a great visual. So we've got our horizontal lines, latitude, and our vertical lines, longitude. The big question now is, how do we use them together to find that one single absolute location anywhere on the globe? Okay, I want you to think back to math class for a second. Remember plotting points on a graph with an x and a y-axis? Well, guess what? This is exactly the same idea. Instead of a positive x-axis, we just say east. Instead of a negative x, we say west. North takes the place of positive y, and south takes the place of negative y. It's that simple. And to avoid any confusion, the format for writing coordinates is always the same, no exceptions. You always state the latitude first, that's how far north or south you are. Then you state the longitude, how far east or west. So for a city like Detroit, you go 42 degrees north of the equator, then 83 degrees west of the prime meridian, and boom, There's only one spot on the entire planet where those two lines cross. But here's where it gets really, really cool. Longitude doesn't just tell us where we are, it also tells us when we are. This grid has a kind of secret connection to time itself. And the math behind it is actually surprisingly simple. So think about it. The Earth is a 360-degree sphere, right? And it takes 24 hours to do one full rotation. So you just divide 360 degrees by 24 hours. And what do you get? 15 degrees. That means for every single hour that passes, the Earth spins 15 degrees of longitude. And that, right there, is the foundation for our 24 global time zones. Now, the direction of that spin is absolutely crucial. The Earth rotates from west to east. This gives us a really simple rule for time. Here's a great way to remember it. East, increase. As you travel east, the time gets later. And west, less. As you travel west, the time gets earlier. It's the whole reason why, say, New York is 3 hours ahead of California. And what's really incredible is that we can actually see this effect from space. This amazing satellite photo of the Earth at night is pretty much visual proof of time zones in action. Look closely here at North America. You can see the city lights are absolutely blazing on the East Coast. That's New York, Boston, Washington, D.C. It is clearly nighttime there. But now, just slide your eyes over to the west. You can see that on the West Coast, in California, the sun is still up. It's still daylight. That, right there, is a 3-hour time difference made totally visible from space. How cool is that? So this imaginary grid of latitude and longitude is so much more than just lines on a map. It's the language of location, it's the engine that powers our navigation, and it's the clock that sets our global time. It is a system that literally powers our modern world, which, leaves us with one final thought. What comes next? What kind of system will we design to navigate the worlds of tomorrow?